Hello students, welcome to EPG Pathshala. I am Dr. Savita Sharma from University of Delhi. Today we are going to discuss about the module Mechanical Properties Part 4 from the paper Electronic, Magnetic and Optical Properties of Materials. So students, let us first see what we are going to learn in this module. We are going to discuss about the impact strength, fatigue and stress cycles, fatigue fracture and failure, mechanism of fatigue failure. Then we are going to see about the fatigue and the fatigue tests, then the design for the fatigue, then we'll discuss the fatigue limit theory. So to start with, let us have a brief introduction about the impact strength. The resistance of a material to fracture under dynamic loads is characterized by what we called as the impact strength. In the SI units, the impact strength is expressed in meganewtons per meter square, which is denoted by Mn per meter square in the symbolic form. It is defined as the specific work required to fracture a test specimen with a stress concentrator. The stress concentrator is a notch in the mid when broken by a single blow of striker in pendulum type impact testing machine. The relation is given by K into C equals to K divided by S naught, where K is the work of the fracture and S naught is the cross-sectional area of the specimen at the notch. Impact strength is indicative of the toughness of the material, that is, the ability of the material to absorb energy during plastic deformation. Impact strength is determined by using a notch bar. Impact tests on a pendulum type impact testing machine. Impact strength of a material varies with certain factors. Number 1, impact strength increases if the dimensions of the specimen are increased. To some extent, the velocity of impact also affects impact strength. Then the third factor is when the sharpness of the notch increases, the impact strength of the material required to cause failure decreases. An indication about the type of the fracture that is likely to occur, that is ductile, brittle or brittle transition, is provided by the temperature of the specimen under test. The angle of notch also improves impact strength after certain values. The next with which we are going to study about is fatigue. Fatigue is the failure of a material by fracture when subjected to a cyclic stress. Fatigue can occur at a stress whose amplitude is much smaller than the static load required to produce fracture. The maximum stress that a material can withstand without failure for a specific large number of cycles of stress is termed its fatigue or endurance limit. Fatigue is distinguished by three main features. The three main features are: number 1, loss of strength, number 2, loss of ductility, and the last one is the increased uncertainty in strength and service life. There are many other situations where fatigue failure will be very harmful. Under following conditions, the fatigue fracture progresses rapidly. The first condition is maximum tensile stress of sufficiently high value. The second one is large vibrations or fluctuations in applied stress. And the third one is large number of cycles of applied stress. Due to difficulty of recognizing fatigue conditions, fatigue failures comprise percentage of failures occurring in engineering. The point at which the curve flattens out is termed as a fatigue limit and is well below the normal yield stress. The fatigue strength is usually defined as the stress that produces failure in a given number of cycles, usually 10 to the power 7. Fatigue properties of a material are affected by several factors. For example, first factor is corrosion. The effect of corrosion is to reduce the number of cycles required to reach for every stress amplitude. We can protect the steel against salt corrosion by chromium or zinc plating. Second factor which affects the fatigue properties is surface finish. Scratches, dents, identification marks can act as stress raisers and so reduce the fatigue properties. It is reported that short peening a surface produces surface compressive residual stresses and improves the fatigue performance. The third factor is the temperature. As a consequence of oxidation or corrosion of the metal surface increasing, the increase in temperature can lead to a reduction in fatigue properties. Fourth factor is the microstructure of an alloy. Composition of an alloy and its grain size can affect its fatigue properties. In comparison to coarse-grained steel, finer grain size steels have higher strength. The next factor which affects fatigue is the residual stresses. Residual stresses are produced by fabrication and finishing processes. Case hardening of steels by carbruising results in compressive residual stresses, and on surface it improves the fatigue. Sixth factor is the heat treatment. This reduces residual stresses within a metal. By producing compressive residual stresses in surfaces, case hardening improves fatigue properties. The seventh factor is stress concentrations. These are caused by sudden changes in cross-section, keyways, holes or sharp corners can more easily lead to a fatigue failure. Stress cycles. Fatigue is caused by fluctuating stresses. The figure given shows the different arrangements of fatigue loadings and corresponding stress cycles. The first part of the figure shows the simplest type of load as the alternating stress, where the stress amplitude is equal to the maximum stress and the average or mean stress is 0. This stress cycle is of sinusoidal for M. The B part of the figure, which is the second part, shows the repeated stress cycle. This type of loading produces alternating stresses superimposed on a steady stress. The maximum stress is equal to the sum of the mean stress and the stress amplitude. The maximum and minimum values can be considered as tensile and compressive stresses about the axis shown by the dashed line. The third part of the figure, which is the C part, shows a complicated stress cycle which is periodic and unpredictable. For example, aircraft wings. Here you can see the figure consisting of three parts A, B and C, showing the stress cycle for testing of fatigue. As I have explained, or as we have seen above, the explanation of these figures, it is showing the stress cycle for testing of fatigues. The A part shows the reverse stress, the B part of the figure shows the fluctuating stress with time, and the C part shows the irregular stress with time. Fatigue fracture. Fatigue fracture results from the presence of fatigue cracks, which are usually initiated by cyclic stresses at surface imperfections. For example, machine markings and slip steps. Although the initial stress concentration associated with these cracks are too low to cause brittle fracture, however, they may be sufficient to cause low growth of the cracks into the interiors. Eventually, the cracks may become sufficiently deep and therefore the stress concentration exceeds the fracture strength and sudden failure occurs. In brittle materials, the crack grows to a critical size from which it propagates right through the structure rapidly, whereas with ductile materials, the crack keeps growing until the area left cannot support the load and an almost ductile fracture suddenly occurs. Fatigue failure. Now we are going to discuss about the topic fatigue failure. One can recognize fatigue failures by the appearance of fracture. Fatigue failure has a number of specific features compared with failure under static loads. Number 1, it occurs at lower stresses than the failure at static loads, which means lower than the yield strength or ultimate strength. Secondly, failure starts on the surface or near the surface locally in places of stress or the strain concentration. Local stress concentrators are formed by surface defect appearing on cyclic loading or notches as traces of surface treatment or the effect of the surrounding medium. Thirdly, failure occurs in a number of stages. For example, first of all, accumulation of defects in the material, first stage. Nucleation of fatigue cracks, second stage. Then the gradual propagation and joining of some cracks into single main crack. And finally, the rapid final destruction. The fourth one is the fatigue failure has a typical structure which reflects the sequence of fatigue processes. A failure usually has the initial zone of destruction, that is, the zone of nucleation of micro cracks, the fatigue zone, and the final failure zone. The initial zone of failure is usually near the surface and has small size and smooth surface. The fatigue zone is the zone where a fatigue crack gradually develops. It has typical concentric ripple lines which are an evidence of jump-wise propagation of fatigue cracks. The fatigue zone develops until the increasing stresses in the gradually diminishing actual section attain a level at which instantaneous destruction takes place and forms the zone of final failure. Now let us see the main basic reasons for taking place of fatigue failures. The first basic reason for the fatigue failure is the surface imperfections like machining marks and surface irregularities. This is the first basic reason for the fatigue failure. The second reason is stress concentrations like notches, keyways, screw threads, and matching undercuts. The third basic reason is at low temperature, the fatigue strength is high and decreases gradually with rise in temperature. And the last reason for taking place of fatigue failure is fatigue strength reduces by corroding environments. Following surface treatments like polishing, coatings, carburizing, nitriding, etc., their effect can be reduced. Now let us study about the design for fatigue. To secure satisfactory fatigue life, it is necessary for one to observe the following points in design procedure. So the first point that we need to observe in the design is to avoid stress concentration by eliminating sharp recesses and severe stress razor, that is the modification of design. Second point is the precise control of the surface finish by avoiding damage to surface by rough machining, punching, stamping, shearing, etc. The third point is the control of corrosion and erosion or chemical attack in service, and to prevent of surface decarburization during process or heat treatment and the surface treatment of metal. The topic is theories of fatigue. There are several theories of fatigue which will concentrate only on few theories here. That is, there are many theories of fatigue, but here, due to the limitations, we will concentrate only on the few theories. The first theory is ORBAN theory. ORBAN theory considers the metal to contain small weak regions. Slip occurs easily along these regions. The metal also contains impurities, that is, inclusions, which acts as notches and cause stress concentration around the inclusion, obviously. In elastic matrix, these regions are treated as plastic regions, which experience increase in stress even when the repeated applied stress is constant. This increase in stress causes plastic strain in the weak region. A crack is formed when plastic strain in the weak region exceeds beyond certain value. Until a large crack is formed, this process is repeated again and again. The next theory is fatigue limit theory. There are some metals which have a well-defined fatigue limit, while other metals do not exhibit fatigue limit. The metals which undergo strain aging have well-defined fatigue limits. The experiment is performed on a specimen in which total nitrogen and carbon content was decreased. Heat-treated steels exhibit definite fatigue limit. This reveals that localized strain aging affects the fatigue properties of the specimen to a large extent. The third theory we are going to discuss is the Woods theory. The strain direction in fatigue is reversed again and again. The slip produced by fatigue consists of slip bands, which are the slip movements of the order of 10 raised to the power minus 9 centimeter in length and 10 raised to the power minus 7 to 10 raised to the power minus 6 centimeter in height. When there is a strain in one single direction, the steps that appear are simple, which we can see in the first part of the given figure. And when the loading is cyclic, the slip bands tend to group as notches or ridges, which we can see in the second part, which is the B part of the given figure. It shows the figure which consists of two parts as we discussed earlier. The first part of the figure shows steps produced due to strain in single direction. The B part of the figure shows when strain is cyclic, notch and edges formation in early stages of fatigue. The next topic is dislocation movement theory. There is a movement of dislocation during fatigue. A localized deformation occurs in the slip bands due to this movement of dislocation. This deformation is called extrusions or rides, that is, some metal is expelled out of its surface. The extrusions are generally accompanied by intrusion, that is the inverse of extrusion, and these extrusions and intrusions are responsible for crack initiation. The next topic is corrosion fatigue. The destruction of the metal under the effect of fatigue may be the cyclic stress or load, and corrosion, that is the electrochemical attack of the medium, is called corrosion fatigue. The endurance limit of metals decreases in corrosion media. Corrosion alone produces pits on the surface of metal. These pits act as stress risers and reduce fatigue strength. The reduction in fatigue strength is much more and crack propagates at much faster rate when corrosive attack and loading occur simultaneously. Now we are going to discuss about the fatigue tests. Machines which may be used for making fatigue tests under cycles of repeated or reversed stress are usually classified according to the type of stress produced. That is, number one is machines for cycles of axial stress, which can be tension or compression. Secondly, machines for cycles of flexural, which can be the bending stress. Third one is the machines for cycles of torsional shearing stress. And the fourth one is universal machines of axial, flexural or torsional shearing stresses or their combinations. So the first test is rotating beam fatigue test. The most common test loading for fatigue testing is pure bending because it is easy to apply. A circular specimen is gripped in collets. The given figure shows the test specimen and main features of the testing machine. The test machine has high speed electrical motor with a speed of 1000 rotations per minute or 1000 RPM. Next to the motor, there is a large bearing which relieves the motor from large bending moment which is applied to the specimen. A collet is attached with the rotating lever arm which is further connected with a small bearing. A force is applied on the bearing which causes the specimen to bend. The revolution counter reader provided with the machine records the number of cycles applied, and when the specimen breaks, there is a counter automatically disengages. As we can see in the given figure, which consists of two parts A and B. The A part of the figure is showing the rotating beam fatigue test machine, which consists of a motor, a holder, a test specimen, and the weights, and obviously the revolution counter and the bearings. The second part of the figure, which is the B part, shows the fatigue test specimen in the bent state. In order to obtain the fatigue limit, that is, endurance limit of a metal, it is necessary to prepare a number of specimens which are representative of that metal. The first specimen of metal is tested at a relatively high stress so that the failure will occur at a small number of applications of the stress. The other specimens of the metal are tested relatively at a lower stress than the previous one. With the decrease in stress value, the life of specimen increased. The number of repetition required to produce rupture, that is, fracture, increases as the stress decreases. Specimen with stress below the endurance limit will not rupture. The life of the specimen is expressed in number of cycles required up to failure at maximum applied force. The results of fatigue tests are commonly plotted on diagrams in which values of stress are plotted as ordinates and values of cycles of stress for rupture as abscissae. The given below figure is the S-end diagram. This curve is called S-end diagram, where S stands for stress and N stands for number of cycles. These diagrams are drawn using semi-logarithmic plotting, that is, plotting N on the logarithmic scale. For metals, for example, mild steel and titanium, the curve becomes horizontal at certain stress. This stress value is termed as fatigue limit or endurance limit. Below this stress value, the specimen does not fail or fracture. That is, the material will not fail even after infinite number of stress cycles. So in the given figure, we can see the SN diagram in which we can see the values for or the curve for mild steel and the aluminium alloy, and we can see their fatigue limits. So students, let us summarize what we have learned in this module. This module gives a brief discussion for impact strength, then the fatigue. We have learned about the stress cycles. Then we have seen what are the fatigue fracture, then the fatigue failures, what are the points which are necessary for the fatigue failure, then the mechanism of the fatigue failure. Then we have studied about the design for fatigue. Then we have learned about the fatigue limit theory. One of the theory that we studied is the Wood's theory. Then the dislocation movement theory. Then we learned about corrosion fatigue. Then we saw the different fatigue tests. Then in the next section, we learned about the rotating beam fatigue test. Then next, the Wöhler's fatigue test. Thank you.